Okay, it is time for the final lesson of the thermodynamics unit, and to close things out, I wanted to take you back to where things began, which is to say, with some stuff that I put in my oven. Let's check it out, shall we? Okay, so this time what I have in my oven are two different pans, and we're going to be testing the ways in which heat is exchanged through different objects. I'm real excited about this experiment because I actually don't know what's going to happen. I have ideas, of course. I could make good guesses, but ultimately I haven't done this experiment. I don't know what's going to happen, so I'm along for this ride with you. The reason why they're both in the oven is that I want them to be the same temperature. And if they sit in there for a long amount of time, they should reach thermal equilibrium. They should be the same temperature as the oven, which is 175 degrees. So every single molecule in both pans should be at the same temperature, 175 degrees. That's the hope, at least. So what you should keep in mind, however, is that temperature being the same does not mean that heat is the same. We've seen that these two things are different. A giant iceberg is going to have more heat than a small amount of hot water. Even though the hot water is much hotter, it has less heat because heat is the total energy of each one of the individual molecules, whereas temperature is going to be that average kinetic energy per each molecule. So they're going to have the same temperature, but that doesn't mean they have the same amount of heat, and that doesn't mean that they're going to give up heat in the same way. So we're going to do an experiment that sees how they exchange this heat in the same sort of environment, in the same conditions, but before we do, I have to tell you about the pans, and I have to tell you about their properties. The pans in question are a stainless steel pan and a cast iron pan. The stainless pan is interesting because it's not one material. It's two sheets of stainless steel with aluminum sandwiched in between. Stainless steel is good because, as its name suggests, it doesn't corrode. Aluminum is good because of its thermal properties. The other is cast iron. As the name suggests, there's no fancy shaping here, they just pour iron into a mold. Cast iron is good because it tends to be cheap, it gets a really nice nonstick coating when well treated, and has some nice thermal properties. I'll talk about them soon. Okay, I'm going to throw some numbers at you soon, but first you have to be familiar with two concepts. The first you already know, which is thermal conductivity. If you remember, that tells how quickly heat is transferred through a medium. So for metal, really high thermal conductivity. Something like wood, not so high. The second you'll learn more about during this lesson. It's called heat capacity. Heat capacity tells you how much heat an object holds at a given temperature. Another way to look at it is how much heat is required to raise an object to a given temperature. You can imagine different materials as having different heat buckets of different size. To raise both objects to the same temperature might take vastly different amounts of heat. They're both the same temperature, their buckets are both full, but the object with the greater heat capacity stores vastly more heat. Okay, so let's talk about some numbers now. Stainless steel has a thermal conductivity of around 25 watts per meter Kelvin, while aluminum has a thermal conductivity of a whopping 205 watts per meter Kelvin. Our stainless steel pan is probably about 75% stainless steel and 25% aluminum, so it's almost like the pan has a value of around 70. The cast iron, on the other hand, has a value of 50. Not bad, but not as much as our stainless pan. As for the heat capacity, stainless steel has a value of about 500 joules per kilogram degree Kelvin, and aluminum has about 921, together making the heat capacity around 605. Cast iron, on the other hand, has a value of 456. So it would seem as though the stainless steel pan wins for all things thermodynamics, but there's one major difference. Cast iron is really heavy. Like, really heavy. Like, really, really heavy. And I know what you're thinking, Mr. Gailey, 5 pounds is not that much. I lift way more than that when I'm lifting weights. And I get that, but what you have to imagine is one, you put more food in it, and so that makes it heavier. And then two, you're not like lifting it from the core of it and move it. That would be easy. What you're doing is holding it from the handle out here, and you're moving it, like you're cooking, you're doing stuff. And then you're like opening up the oven door and you're doing stuff, and it's hot and it's dangerous. So it's a heavy pan. It's a heavy pan. It's a little unwieldy. It's heavy, okay? That's all I'm saying. Man, I need to work out more. Right, so the stainless pan is only about 1 kilogram. That's 2.2 pounds. But this cast iron pan weighs 2.35 kilograms. That's about 5.17 pounds, more than twice as heavy as our stainless pan. So even though the materials in our stainless pan together have a greater heat capacity than cast iron, about 30% more, because our cast iron is so much heavier, it still holds nearly twice as much heat. All right, so this brings us to the actual experiment, what we want to test and what we want to see the behavior of. I'm going to pull out both pans from the oven at the same time. They should be both at 175 degrees. I'm going to take them, I'm going to place them on the countertop right here in front of me. Then I'm going to grab ice out of my freezer and I'm going to put equal amounts by weight into each pan. The question then follows, what happens? More specifically, what is the behavior of the melting of the ice in the two different pans? Is it going to be the same? Is it going to be different? If so, what will be different about the way that it melts? Keeping in mind that our cast iron pan has much less good thermal conductivity, but has a greater heat capacity, whereas our stainless steel pan conducts heat much more thoroughly, much more quickly, but it can't hold as much heat. With this in mind, you have to guess what's going to happen. So, with nothing else holding us back, I'm just going to go and grab the pans. I said, with nothing holding us back, I'm going to go ahead and grab the pan. What is that noise? Oh, right. Before I grab the pans, you all have to make predictions. And of course, I'll wait. So now that it looks like things have stopped changing appreciably, I want to get some sort of quantitative data on which melted more ice, essentially. So what I'm going to do is use a colander and strain out all of the melted water, leaving behind the unmelted ice. I can then weigh this and see what was left over, what was unmelted in each case. So for the stainless steel pan, it had 0.792 kilograms remaining. That's ice plus the colander. And then I'm going to repeat the process. I'm going to do the same thing to see how much ice was left over with the cast iron. So repeating the process, using the colander, I'm going to strain out the water from the ice. I cover up the scale here accidentally, so I'll just tell you that it reads 0.714 kilograms. And that's 0.078 kilograms less with the cast iron. Okay, let's talk results. It seems as though after the water was drained away that the cast iron pan melted an additional 0.078 kilograms of ice over the stainless steel pan, which probably makes sense, right? We know that the cast iron holds more heat and therefore has more heat to dump into the ice, melting it. However, an astute observer might have noticed some other curious things happening, especially right at the beginning of the video, that speak to the thermal properties of the two pans. I personally can say I was surprised at a couple different things in this experiment. For example, I thought that the ice would be melting for a longer time than it was, like maybe 3, 4, 5 minutes. But really, after like the first minute, it was done. That was about all it took for the metals to come into thermal equilibrium with the ice and the ice water. So we're closing out our thermodynamics unit. I'm hoping you learned something both today and throughout the unit. I think a lot of this stuff is really interesting because I like to cook. And I think thermodynamics is one of these sorts of sciences that can really inform your cooking and make you cook better. If you take cold food and you put it in a hot pan, you're going to cool that pan down. However, if your pan has a greater heat capacity, it won't cool it down as much. And if you understand these sorts of principles, it allows you to choose the pans, the equipment, and the settings for your cooking to make your food better. So thermodynamics comes to a close, but another unit awaits.